Hey dear students, this is Pradesh Chaudhary Quantum Group. Let's see this very beautiful question of Pathfinder from Kinematics chapter. It's MCQ question number 20. So the question states a horizontal wax bar B rests between a wedge and a vertical wall as shown in the figure. The wedge starts moving towards the wall with a constant acceleration 0.5 mm per second square. The moment the wedge starts moving, a continuous supply of heat from the wall starts melting 1 mm length of the wax bar per second. If the bar always remain horizontal, which of the following conclusions can you make? Okay, we'll see the options one by one. First of all, let's see the constant part. So this is the diagram and we want to look from the ground frame first. So this part of the wax bar is just joined by that fixed wall, and wall is fixed, so this part of the wax bar is not moving. Wedge is moving with a uniform acceleration 0.5 mm per second square. So because of the wedge and they have to maintain contact, so this line will also move. Alright. Not all the points of the wax bar have the same velocity, so this is for the wax bar, so the velocities that I have written is for this line, the line that is in contact with the wedge. So because this wax bar is melting, its length is reducing, so after some time the length would be here, this would be here, so basically this edge is moving in this direction and it is melting at the rate of 1 mm per second. So this ux is equal to 1 mm per second. This is my x direction, this is downward is the y direction. And suppose it has a acceleration ay, the wedge has the bar has acceleration ay, and that is for the wedge constant. You can assume in the downward direction, automatically you will realize that you are wrong and will show why it is in the upward direction. So ux we have got thing, and this acceleration of the bar is acceleration of the wedge is 0.5 mm per second square. Now see with respect to wedge, first of all the velocity part. At the initial moment this wedge was at rest, so if it would have been moving, so we have to add a negative of that velocity to the bar, but because it was at rest, so whatever velocity was of the bar in the ground frame, that is the same with the respect to wedge at that moment, so that is ux and uy. And the wedge constant requires that for two bodies to remain in contact, there should not be any relative motion normal to the common contact surface, and this is a normal common contact surface. This is a common contact surface and this is a normal. So along this direction there should not be any relative motion. So the component of ux along this direction and components of uy along this direction must balance. So component of ux along common normal is ux sine 37, and component of uy along the common normal is uy cos 37. So equate them. Uy cos 37 is equal to ux sine 37, put ux is equal to 1, simplify, we will get uy is equal to 3/4 mm per second. And now let's see the acceleration part. Acceleration of B I have assumed in the upward direction, you can assume the downward direction problem, but see. So and with respect to wedge I am looking, so ABA is equal to AB minus AA vector. So if I look in the wedge frame, so it will also give its acceleration the opposite direction to the wax bar, so minus 0.5 in this direction. So these acceleration AY should be such that again there is no relative acceleration normal to the common contact surface, otherwise they will either separate or press. So suppose if AY I had chosen this direction, so there would be both AY and 0.5 will have a component along the normal, so the normal component will not cancel, but what is required that there should not be any relative motion along common normals, hence AY should be like that. So for no relative acceleration along this direction, component of ay along this normal and component of 0.5 along this normal should be same. So what we'll have, we will have ay cos 37 is equal to 0.5 sin 37, and to simplify that thing, we'll get ay is equal to 3 by 8 millimeter per second square, and this is the uniform acceleration. Now we can proceed to check the options. So initial moment we have, now this is with respect to ground frame. Initial moment, the at the initial moment, this uy was the wax bar had a downward direction acceleration, downward direction velocity equal to 3 by 4 millimeter per second. Ay is in the upward direction, so taking this direction as a positive, that is a minus 3 by 8 millimeter per second, and that is square. Right. So this is a classical case of turning. The acceleration is uniform and initial velocity is opposite to the uniform acceleration. So this wax bar along y direction will go down and then will reach to a momentary stop and then will turn back. Turn back means turn up. The first option, that is perfectly alright. The bar first moves downwards then upwards. And at what time the bar stops? So this option is correct. This is a correct option. Now the bar will stop for the option B. The bar will stop when Vy is equal to 0 along y direction we are looking. So apply the first equation, Vy is equal to uy plus ayt, and Vy is 0 when it stops. So uy is 3 by 4, ay is minus 3 by 8. So that gives t is equal to 2 seconds. So at t is equal to 2 seconds, the bar stop for a moment from the beginning. So this option is also alright. And now see the motion of the bar along y direction. We are looking for the option C and D. At t is equal to 0, the velocity was in the downward direction, acceleration was uniform opposite to the initial velocity. So it will come to stop here, and it is like a motion of gravity. If you throw something upward, it goes up and then downwards. Time taken from the moment of projecting till the maximum height is same as the time taken from the maximum height to the initial point. So it takes 2 seconds to come to a stop, and then 2 seconds again to reach the initial point. So for the 4 second displacement is straightforward 0. So that is wrong. C option is not right. For the D option, displacement in the first 4 seconds, from the symmetry we can see that you just get the distance traveled in the first 2 seconds, then just multiply by 2, because whatever distance is from here to here, the same is from the returning. So for that thing, displacement of first 2 seconds, apply the second equation of motion as equal to u plus v by 2 into t. U was the 3 by 4, v is 0, and t is 2 seconds, we get 0.75 millimeter. So total distance is twice of that, so that would be 1.5 millimeter, and this is not the right answer, but they have given a right answer. But you see that, and that was a misprint in the Pathfinder. Now if you can check the latest edition, so they have corrected the printing mistake and there is a 1.5 millimeter written. So that is a correct thing. Thank you.